you for the introduction. I'm QunaSys CEO and co-founder, Tennin. So today I would like to talk about the beyond VQE. So kind of the VQE is the algorithms that the chemistry we can run on NISC, but kind of as talking keep quantum, so kind of these algorithms kind of has a lot of limits. So kind of we would like to share kind of what we are doing beyond these algorithms. Okay, so kind of to start with, a little bit before going to the topic, we would like to talk about our companies. So QunaSys is founded 5 years ago, and we are based in Tokyo, Japan. And we are founded with the Keisuke Fuji, so one of the faculties in the Osaka University. And currently we are 45 members, and kind of we are focusing on software R&D for use for quantum chemistry calculations. Okay, so what we are doing is like maximize the power of the quantum computing. So there's a lot of interesting quantum computing hardware. So kind of what can we take the best from this hardware? That is what we are focusing on. All right, so kind of in QunaSys, we are not just doing algorithms research, but we also start from the teaching industry. What is quantum computing? Why this device can do the chemistry calculation, for example, and then goes to we work with end users to find use cases together, and kind of when we find interesting use cases, like implement algorithms and take benchmark and testing that algorithms. And then kind of currently, the quantum computer has even algorithms has a lot of limitation. So kind of how can we make the better algorithms is really keen in this field. So kind of explore the new algorithms with ourselves and with our university, other startups, and of course hardware vendors and the community. So that's a brief picture of what QunaSys is doing. So kind of get to the points about the variational quantum eigensolver. So the VQE is called the variational quantum eigensolver. So I think it might be most of you already understand these algorithms, but kind of this is algorithms that you tune the parameter inside the quantum circuit and variationally get the ground state of the molecular energy. Kind of that is what we kind of based on these algorithms. So kind of get one parameters and input to that to the execute on quantum devices and get sampling result, and then tune the parameter and get the better energy. So that is what this VQE algorithms is. And kind of what QunaSys have been doing is like expanding these VQE algorithms. So for example, as I mentioned, like the VQE can get the ground state energy, but kind of what we can expand is calculate the derivative of the energy that gives you force of that applies to the molecules. So that enables you to do molecular dynamics simulation. This will be important for pharma application. And other is like not just calculation of the ground state energy, but also calculate excited state energy to simulate OLED or solar cells. And other is like the solid state material. So not just the simulation of the molecules, but also simulation of the periodic systems like the metals. And kind of we have developed algorithms to calculate band gap, for example, for that. So that is what QunaSys have been developing. But kind of, I think you say like people say like the NISC is dead, or like, and in this article it's like said NISC is dead and dying, and NISC is dying, NISC is dead, and also thankful for him that he also write in Japanese like NISC sayonara, sayonara NISC era. So kind of like a lot of people kind of start saying this, and also about the VQE. So kind of a lot of people saying VQE is dead, NISC is dead. So kind of I want to talk about this. So kind of VQE, I agree this is maybe dead, fortunately. So I don't believe like the using VQE algorithms just by itself purely we can solve industrial application in the time frame in the near term. But kind of what we believe is like, since we have a lot of interesting hardware, like 400 qubit devices we already have, and this year we will have thousands of qubit superconducting devices, and we will have high fidelity ion trap devices. So kind of how to leverage that is still unknown. So kind of I want to question, is NISQ is really dead? So kind of what QunaSys is doing, is working on how can we make the best from these NISQ devices. And I would like to share about some of the recent research that the QunaSys is doing. So kind of since we found it, we have 37 papers published. So kind of why the VQE is dead, I want to talk about that. So kind of in the variational quantum eigensolver, so you need a large number of shots to get the energy, and also a lot of steps to update the parameters. And it's known like if we have more qubits, it's kind of exponentially difficult to steps we need to get the good energy of the molecules. So kind of we see a lot of challenges in the VQE here. So kind of what QunaSys is doing, I would like to share our 3 papers from the QunaSys. The first is called Quantum Selected CI. So this is inspired by ASCI in the classical quantum chemistry method. So kind of what we are doing is like we do VQE until some extent, but as you see the green line in the top, like just doing VQE and with update, it won't get to the energy, lower the energy that much. So kind of what we do is in the middle, just use quantum computer and sampling the states from the quantum computer, and then use classical computers to diagonalize that large matrix from there. So kind of giving you the example is like, for example, we do VQE until this point, and kind of we do get this green result. But after this, we won't do VQE, but just sampling from this state and do classically diagonalization of the sampling result, we will get much lower result. And if we have using other methods as an input, if we have a better result as a quantum state input, we get much better the result by the classical post-processing. So this is one thing QunaSys is developing. And other is like local variational quantum comparisons. So this is algorithms to simulation of the time evolution of the Hamiltonian. And kind of how we do is in the right. So kind of if you do simulation of time evolution, normally you do a total expansion, but that will take a lot of long circuits. So what we do is like the variationally learn what the that Hamiltonians, and kind of do simulation of time evolutions using that. So kind of, but this, this goes back to the VQE is dead. So kind of, if it's using a large system, it will be variationally hard to tune the circuit. But kind of the point of this paper is like we can locally compile this. So we don't have to variationally tune the parameter of whole system, but actually we can just tune in a small part and then implement it in the larger system. And for example, calculation of the Green's functions, that is important to understand the periodic systems. So kind of this is research done with QunaSys and Osaka University, and based on that we are have a recent paper with Fujitsu on this. And lastly is about the quantum Karp-Martinez molecular dynamics. So this is inspired by Karp-Martinez method, and kind of this is, goes related to this morning's talk by Beringer Ingenheim. So kind of he is mentioning like the getting 1 point of the energy, it take like for example, like 3 days, and kind of that is same with these algorithms, but kind of what the point of these algorithms is like once you get the state of the molecules, so you can kind of use that state in also in the next state. So you can how to say kind of when you once got the energy and the derivative, so you can just using that parameter to update. So you don't have to each time variationally tune the parameters. So that is kind of the core of these algorithms. Okay, so kind of would like to kind of summarize this. So kind of NISC, so we believe there's kind of not just using pure VQE, but kind of expanding this, fundamentally improve these algorithms. We can improve to some useful applications. And also what in QunaSys is doing is also doing we call pre-FTQC. So for torrent quantum computing algorithms, if we want to execute that, we need like millions of qubit, but kind of we will have 1,000 or like 10,000 qubit, and kind of it might be we cannot do the perfect error correction with that. But for example, like the kind of current quantum computing, it's have a really good 1 qubit fidelities, and kind of we use that use noisy rotation and with using error correction in Clifford operations. So kind of this kind of techniques, so something between noisy and doing partial error corrections, that is also some techniques we are developing. Okay. So kind of talk about a lot of research, like making the new algorithms and kind of testing that with users and see if this is really industrial usable. So that is kind of a research aspect of the QunaSys, and I would like to cover the education's part of what we are doing in QunaSys. So kind of QunaSys started this QPark, the Quantum Practical Application Research Community from 2020s, and it has more than 50 companies, and mostly it's Japanese companies currently together. And what we are doing in here is, for example, the first one is like, okay, quantum computing. So we every day have dozens of the archive paper. So for end users, it's really difficult to catch up with this technology. So kind of we are sharing the newest update of this field. And also the kind of that 50 companies work together and doing networking and collaborations with each other. And also what QunaSys is offering is like we are making learning materials for them. So even for the new people interested in this field, so kind of they with our learning materials, they can understand what is the quantum computing, how the hardware works, and why these devices can do the first principle calculations. And then after they understand that, kind of we do workshop to talk about use cases, and they can use, for example, maybe clicker is dead. Okay, so kind of number 4 is a simulator, and the number 5 is using the real quantum computer. So yeah, that is kind of what we can do in QPark. Can you change clickers? It's dead, seems. Yeah, maybe if you can switch to the next slide, yeah, that will be helpful. So kind of in QPark that we originally started in Japan, but kind of we are, yeah, next slide please. We are expand to the Europe this year. And actually, it will be in the kickoff event will be in 2 weeks. So kind of, I would like to people kind of interested in start quantum computing in chemistry field, or like if some of your team is new to the teams and have quantum chemistry expert but not quantum computing expertise, like they come to the QPark and learn the basics of the quantum computing to the state-of-the-art algorithms. That also includes the algorithms I pointed out here. Okay, and so kind of that is program you have, and kind of for QPark, if you are interested in, the Shino is sitting there, yeah, sitting in the back. So kind of please contact her, or or the qpark.qnasys.com to access our homepage, and you can get more information about what we are doing in QPark. Okay, so that 2 topics is mostly for the industrial members. So what's the QunaSys algorithms research going on and kind of educational offering we have. And the last thing is would like to talk about the quantum computing communities for the people doing quantum computing algorithms research, what QunaSys is doing to boosting that researches. So kind of QunaSys have been doing the quantum computing algorithms challenges, and like the last time it was more than 180 participants on there. So kind of, I think we have a lot of things to learn from the machine learning. So it's not like we using quantum computer, we can make next ChatGPT, and I don't know how to do that, but actually more how the quantum computing, machine learning communities evolved in a bigger perspective. So this is an example of the ISVRC. So kind of it's called the ImageNet classification challenges. So kind of how do you do is like to have 1,000 classes of the problems and do the classification and kind of use the machine learning techniques to do classification of the images. And when it started in 2010, it has a 28% of error that this classifier make mistakes, and the next year it's like 26%, so increased by 2%. But you can see in the 2012 it dramatically increased to 16%, and everyone knows. So this is due to the neural networks and by Jeffrey Hinton's group, and we can see that this the machine learning algorithms dramatically improved. And kind of I want to say kind of there's a lot of papers every day of quantum computing algorithms, and they say they have a state-of-the-art techniques, but kind of it's really difficult to, and if we implement that and we find something that other part doesn't work, so kind of I think it's really important to all have same measures and measure the algorithm's performance in the same. So that is what QunaSys have been working on. And kind of from this May, we are studying the quantum algorithms grand challenge. So kind of like to, for the chemistry companies or like for the consortium people or universities professors, like the form a team and kind of make the state-of-the-art algorithms and like compete on the algorithms benchmarking. So kind of I think that is the one way how the science progressed, and we would like to help to boost the scientific innovations. So kind of it's more easier to go to the Quantum Algorithms Grand Challenges website, but kind of the basic idea is like a really basic of the quantum chemistry. So kind of get the ground state of the energy, and we are a calculation of the Fermi-Hubbard models, and we have the prove that this resembles the molecular Hamiltonians. And then also other part is like we can have the method to know exact solution of this. So exact energy of a Fermi-Hubbard model. So kind of, and to compete with getting the more accurate energy in limited execution times. So that is what we are hosting, and kind of it will be like 3 months challenges, so from May to end of July. So please submit your result by end of July, and kind of everyone is welcome to here, and kind of we would invite the winners, top 4 winners, to IEEE Quantum Week. And yeah, if you are interested in, please access the QA.gc.org, so Quantum Algorithms Grand Challenge.org. Okay, so lastly but not least, so kind of it's almost end of the Q2B Paris, and kind of QunaSys and with QCware, we will host other Q2B. It will be Q2B Tokyo, so everyone will be also welcome to there. Thank you.
Thanks very much, Tennin. Is there any questions from the audience? Time for a quick one. I had a small question. I was wondering about the local variational compilation work you did. I was just wondering how local is local? Is it like a constant or?
I think it's trade-off. So like if you do really small, it might be difficult to generalize.
So it's a heuristic more than.
Yeah. We don't have much, how to say, guarantees of the error. Using that. So it's that's
okay, perfect.